let's wrap things up for today. We have had a long day. We've covered a lot of material. We've gone through communications, architecture. We talked about Kubernetes, about hosting, about orchestration, about microservices. Let's talk about one more big area, distributed data. And when we think about distributed data, in microservice applications, the best practice is each microservice owns its own data store. So you hear the term database per microservice, and this might be the hardest part, maybe, for a lot of people. So again, we think about a monolithic database. Things are kind of simple in life. So we have, again, monolithic application. Monolithic applications typically have a nice shared database. Everything in the app shares the same database pretty much. Typically it's relational, right? So what does this mean, man? This means, you know what? Very straightforward. I can query multiple tables across the database very simply, select everything from customer, join orders, join order details, boom, there it is. Even more importantly, I can invoke ACID transactions. I need to update order detail, and customer. At the same time, everything commits or everything rolls back. So again, I'm always consistent. I get immediate consistency. Single resource to manage. And again, usually I'm going to scale up. So scalability in relational databases are typically not out, but it's going to be up. I'm going to throw more and more hardware at my database. They don't scale horizontally well, but scaling up is usually the way. When I move, though, into a world of, let's take a look here, what's going on. When I move into a world of microservices, life becomes a little bit different. If I follow the best practice of each service having its own data store, then pretty much here, I'm moving into a situation where, yeah, my services are loosely coupled. The data and the service can evolve independently. I can avoid data model conflicts. If I make a change here in this database, I'm not going to break things in another database as long as my interface stays the same, doesn't change. I can reduce some of the contention and some of the competing reads and writes. So again, when I have a single relation database, again, I'm doing reads and writes, I'm going to see contention, right? I'm going to see locking. If each service has its own data store, the databases are smaller, they're more simple, and again, you can scale each one individually, and you're moving away from that contention of reading and writing. We also get into a situation, too, of polyglot data. We've been talking about this. Each service, if it owns its own data store, can select the best data store that for it. So one service may say, hey, I need a relational database that represents my data the best. Another may think about using maybe a NoSQL. Another may do a simple key value pair like we see in Redis. And some databases, like we'll see now in a little bit, may actually have multiple data stores. They may split the writes and the reads into two different data stores. And again, you might see here we might maybe use a SQL database for our writes and maybe a Cosmos database or something else for our reads. So again, let's talk about this. When we introduce this idea of a database per microservice, there are a couple of things we need to think about, though. A couple of big challenges. Challenge number one is this. What about queries across distributed stores? So if I have individual services, each service has its own store, I need to query data a little bit from this service, other data from that service, and maybe data from a third service. How do I do that distributed query across all those services, right? So here's an example here. Let's think about the shopping basket service. What does it own? Its data store, pretty much, it is system of record for shopping basket data, and probably line item data. It owns that data. But you know what? Here's the problem. Shopping basket service, in order to add an item to the basket, it needs to know a couple of things. It needs to know information about a product, okay? And it also needs to basically to calculate a discount price or price for a customer. The problem is shopping basket doesn't own product data, and it doesn't own discount data. So how does it handle this? Well, we could have the shopping basket, like we said, do direct HTTP calls, synchronous calls to the catalog service. I'm going to add a line item to the basket, call the catalog service, do a product lookup, call the discount service, calculate the discount. So I can do these direct calls, and they're fairly simple to code, but we said doing direct HTTP synchronous calls in across microservices is not a good practice. Again, a lot of things can go wrong here, and even best case scenario, we're going to experience it's going to impact performance, and it can certainly impact reliability as well too. So what we could do here maybe is this. What if we were to take the data from the catalog service? Because if you think about the shopping basket service, it only needs a couple of data items from the product. So if catalog service owns product data and shopping basket needs product data, shopping basket just needs a very small subset of product information. It doesn't need all the product data. So what if we were to denormalize and take just the product data that shopping basket needs and copy it and put it right in the actual shopping basket itself? So we could build what's called maybe a product read model. It could be in the same data store. It could live in the shopping basket service. Now shopping basket service says, hey, you know what? When I want to add an item to a basket, I can do a lookup on that product, but that data is right, in process with me. It's very quick, it's very fast, it's dependable. I'm not calling the other service to get that. So again, this is called the materialized view pattern. It's a best practice that we see across microservices. And again, this is where a service needs to own data or use data that another service owns. It's more efficient typically and a better practice to put a copy of that data into the actual service itself to avoid those synchronous, direct, cross-service calls that can get us in trouble. So again, we decrease the coupling, and now we have locality, meaning the service is in the actual process. We improve response time, we increase our reliability. We're getting rid of that coupling on there. However, then the question becomes this. The question becomes, if we do that then, right, okay, what about the discount service? Well, in this case, we're probably still going to need to keep this call to discount service because we're not necessarily getting data here. We're actually having the discount service, we're actually invoking a method and having a discount service do a computation. So in this case, we're probably not going to move the discount data into the shopping basket service because there's actually a computation involved. But we might here, instead of doing an HTTP call, we might do maybe a gRPC call, seeing if we can speed up this process possibly. So your question might be this. So this is how the materialized view pattern would look. So again, we said initially we're going to move product data or a subset of it into the shopping basket service. It might look like this. So here's our normalized products data coming from the catalog service. We have a product has artists, and a product has genres. Think of a product as a music, as a song. So what if we were to denormalize just that data we need and move it right into the materialized view pattern, so that way not only is the data in the shopping basket service, but it's very easy to query because it's all in a single denormalized representation. We're not having to join tables together. If you want information about song 1, here it is. Information about song 2, here it is. We're not having to join these all together. So again, this idea of a materialized view pattern becomes a best practice in here. And how do we the problem is we have duplicate data now, right? So we have data in product. We have the same data in product and the same data in the product read model for shopping basket. So again, if this were a monolithic application, duplicate data would be considered a bad practice. We don't have duplicate data typically in a single shared relational database. But in a microservice, this is considered a good practice. Again, a small denormalized copy, and again, in this case, the system of record for any product is always going to be a catalog service. Any change we make, we're making it in the product database in the catalog service. What we're going to do here is we're going to set up a pub/sub messaging pattern. So whenever we make a change in product, whether we add a new product or change a product or remove a product, we are going to publish an event to a message broker, maybe right here, and then the shopping basket service is going to subscribe to that event, and when that event happens, it's going to grab it, and at that point only, when it's told to by catalog service, will the shopping basket service update its product data. So again, this again is talking about how we keep these things consistent. So case in point, When one service needs data from another service, we think about moving a denormalized subset of a data into the service that needs it, and then we keep these in sync by setting up some type of messaging between them. Keep in mind, key thing here, catalog service owns product data. The product data in Shopping Basket is nothing more than a copy. So again, catalog, it manages product, it owns product. It is only when catalog sends a message to change product data to all the read models that this read model gets updated or changed. So again, let's get through this. That's basically how we deal with querying. What about transactions? What about that? So all of a sudden now we have many services, and we're going to perform an operation. And in this case, we have to actually, we need to commit across many services. So here's a scenario right here. What if we did this? What if we're going to check out, right? And what if that checking out process involved this? We would basically create a pending order in the order service. Next, we would validate the payment in the payment service. Once that's complete, we would build the order in the build service. Then we would basically distribute the order. This might be the shipping service here. And then finally, we would send an invoice in the notification service, and then go back and go back to the order service and mark that order as complete. So you can see we got 1, 2, 3, 4, 5 different services. Oops, I think we need to mute Manu maybe in the background. So, so we have 5 different services here, and what's going on is we have pretty much each one of these services needs to participate in a transaction, but there is no such thing as a distributed transaction for them all. This could be a SQL Server database, this could be a Cosmos DB, this could be Redis Cache. So again, there is no distributed transaction. This is where we think about the Saga pattern. So the Saga pattern is a very common practice or common pattern in distributed applications. It enables you to programmatically create a distributed transaction. Again, this is a lot of work, okay? But this is how typically people do it, right? So here's the Saga pattern. Look what's going on here. What do we do here? We start our transaction. We create a pending order in the order service. And again, then we commit. So the data store in the order service, we commit the transaction right here, and we say this is done. Then we publish an event, and then maybe the payment service listens to the create order event. It grabs the information, it validates the payment, it updates its data store, it commits, then it sends an event. The build service listens for that event. It subscribes to it. It then builds the content that we're going to ship, updates its own data store, and commits. Then it publishes an event, and the distribution service, then this might be our shipping service, the name for it, listen for the build event. Then it would basically set up the distribution of the shipment. Then when it's done, it publishes an event. The notification listens for that event, notifies the user, sends an invoice, does an update in its data store. It sends basically an order complete event, and then that goes, and the order service listens for the complete event, grabs that, marks the order complete pretty much, and we're all done. So again, notice the steps in here. We have 1, 2, 3, 4, 5, 6 individual transactions, okay? Independent transactions that take place within this larger, ordering process or create order transaction. Notice your red stuff too. So here's the trick. As we're going through each step, we create the order, we update, we validate the payment, we update, we build the content. If something goes wrong, say for example in the distribution service, something goes wrong and we can't ship this, then we need to back out each one of those transactions. So notice in red, we have compensating transactions. So if the distribution service here, if it were to publish a cannot, distribution failed event, we would remove that distribution. We would publish an event here, the build service would grab, it would remove the content, it would publish an event, the payment service would grab, it would cancel the payment, it would publish an event that the order service would then grab, and then the order service would cancel the order. So you can see the complexity in doing transactions across multiple services and trying to keep them within a larger transaction scope. So again, the Sega pattern can be your friend. I won't spend too much time on it here because we're getting kind of late. I'll just tell you a couple of things about it. It can be implemented two ways. We can do events, which would be considered a choreography implementation, or we can do commands, which would be more of an orchestration implementation. If we were to do a Sega with events, what we're going to pretty much see is what we just saw here. We're going to see every time, the order service or the payment service, the bill service, we're always we're publishing events and other services are subscribing to them. We're basically able to build through this. We're also able to have events that pretty much, if we hit a failed event, we're pretty much able then to call the other services and have them back out whatever they did. Back out the order we built, back out the payment, cancel the order, and send a notification to the customer saying, we're really sorry, we can't process this right now. We'll get back to you later. So this is using a Sega pattern with events. We can also do a Sega pattern using orchestration. We can have a single class that pretty much orchestrates each one of the events. So in this case, we basically say the cart service says, you know what, I'm sending a checkout event. The order service creates this orchestrator class. And this class pretty much is I'm going to push a command into the message broker for the payment service to do to validate the payment. Then I'm going to push a command into the message broker, a build order command for the build service. When that completes, I'll push a command for the distribute order, for the send order, so on and so forth. So again, here we're just using commands. We have a centralized orchestrator. So instead of using independent events, we're orchestrating it using, again, commands. So before we were using events and topics. Now we're using commands and we're using pretty much here queuing pretty much on this. We're able to queue each one of these events for the order to listen to. And again, we can also have a compensating logic in this orchestrator that basically begins to back out. We can have commands that build things, and we can have other commands that back out things we've already done if something should go wrong on this. So again, you can see the complexity here, but this is typically how it's done. So when we're thinking about doing a transaction in a microservice that basically involves many services, we're typically looking at doing a Sega. So here's what we're going to do. We don't have one yet in the application. Here's the plan for the one we're going to do. You can see we have here is our shopping basket service, our ordering service, our payment service, our shipping service, our notification. You can sort of walk through. You can kind of see that the shopping basket would do a checkout. It would publish that event. The ordering service would listen to the checkout event. It would create the order. It would then raise an order created event. The payment service would subscribe to the order created event. It would validate the payment, charge a customer's credit card. If that's successful, it will publish a process paid event. The shipping service would respond to the event. It would ship the actual order, come around, complete the order. You can see the different things. You can also see here too if any one of these services failed, right? Say for example we can't ship it, then we're going to remove that shipment. We're going to publish a shipment canceled event. Then we're going to basically cancel. We're going to cancel the payment. We're going to publish a cancel payment event, so on and so forth. We're going to back out of this thing step by step by step. So the idea here is if we back out of it, when we get back to the shopping basket service, we're in a consistent state. Anything that we change in the other services, we have basically rolled back using this Sega pattern. So again, it's kind of a lot to go by. We're going a little fast, but I want to make you aware of this. This is typically the best practices for doing these things. So again, we're using materialized view patterns when we're querying across multiple services, and when we need to implement a distributed transaction across multiple services, we're looking at writing a Sega pattern. You can write your own Sega pattern raw like we're doing here. There are some frameworks that help you do that as well too on here. Let's look at one more thing. I know it's getting late. Everybody's tired. Let's look at one more thing. We've had some requests to talk about CQRS. Let's talk about that here really quickly. So we have these scenarios where we may have high volume data in cloud native applications. So again, these large microservice cloud native apps, they often support high volume data requirements. We got to be careful because sometimes, traditional data storage techniques can cause bottlenecks, right? But for complex systems that deploy on a large scale, we're going to look at a pattern called CQRS to help with that pretty much. So CQRS pretty much, so for normal scenarios, when we're doing, we have a service, we typically have a single data store. And in that data store, we have, whatever tables, we have documents pretty much that contain each transaction. So in a normal scenario, we have a single model, a single repository, and a single table, whether we're reading or whether we're writing. So again, if we're reading, we're basically pushing things out, we're writing. But when we get into these high volume data scenarios, we might benefit from a model where we separate the reads from the writes. So look what we're doing here. In this particular data, in this particular service, okay, this is probably going to be a single, it's not every data entity, but maybe one of our data entities in here, which is very, very busy. Maybe this is our order. We're going to have a separate data store for the reads for those orders and a separate data store for the writes, as well as a separate model for command, for the writes and for the reads as well too. So anytime we're doing and write and update from the, what do? We go through the command model and we go through the entire, we go through all of our domain logic, everything's applied, and we end up writing that data to the write store. This is a system of record. However, we don't want to always be reading from that write store, especially if we have a high volume of reads, because we're going to get contention. We're going to be locking as we're updating and trying to read that. So what if we had a separate read store? Maybe this read store did nothing but read. So here comes a query from a user, the read. We route it to the query model, which is a very lightweight data model. We go out and we grab the data they want. This data is typically denormalized, so there's not a lot of table, there's not a lot of joins here. We're storing this data in a format that's very easy to read. So again, this is where we're going with this idea of CQRS, a separate write and a separate read store. So again, this is known as CQRS, or Command and Query Response Segregation Pattern. This gives us the ability to separate our reads and writes and scale our reads and writes as well too. So here would be, like we said, here's a read operation in a CQRS. Here's a client request, calls the controller, says, I need to get information about an order. We're going to typically call a query handler. The query handler calls a repository. We do an RRM, but we're basically querying the data store. Here's going to be our read data store. This should be denormalized. It should all be very fast, very lightweight. We shouldn't see a lot of business rules going on there. This should be very, very quick, highly optimized here. This would be our reads. If we're doing our writes, that's going to be a little bit different now. So here come our writes. So now we're going to go to a different write store. When we're doing writes, we're going to route we're going to route that message through a controller into a command handler. Here we're going to go through the actual domain layer. We're going to apply all the business logic, all the validations, all the rules for that write to make sure that data is perfect. Then we're going to call the repository. Then we're going to end up inserting, updating, or even deleting that particular write into the data store. So again, we're separating here on this. We keep the reads very lightweight, very easy. We keep a lot of the business logic. We keep a lot of the business rules out of it. Just get the data back as fast as you can, right? But under writes, we're very concerned about applying all the business rules, all the business logics, so on and so forth. So again, it's a different model, a different process here. What we do with these two is this, though. Notice how we have whenever we make any kind of change to the write table, which again is going to be our system of record, we have a process that we replicate that particular, we take that write information, we probably denormalize it, or we transform that data into a denormalized representation and shove it into the read table. So whenever we make a change to the write table, we're going to update the read table. But again, typically the read table is going to be in a different format, a much simpler format. And again, typically here we're looking at eventual consistency, right? So you make a change to product XYZ, and then the write table is going to push that change into the read model. There's going to be a very short lag here. This is going to be our transaction lag. This might be milliseconds. It might be seconds. It could even be a couple of minutes if things are very slow here. There's always a chance that if we make a change to, say, a product, and then the user immediately queries that same product, and we haven't replicated that change, the user is going to see old data, okay, or stale data. We're not going to see the change quite yet because it hasn't replicated yet. So again, that's one of the constraints that we have to deal with when we're dealing with separate logic like this. So again, this would be an idea of write versus read on this. So again.
So Rob.
Yes, go right ahead.
An example that I've shared with folks about the eventual consistency. If you go back to the last slide,
sure.
And let me know if I'm thinking about this right. Is the right store? If you think about your bank register, right? The right store is the authoritative log that your bank has on your checking account, and the read store is what the ATM machine has, and it doesn't reconcile that until what, like 2 a.m. Right? So it decides, yeah, I can give Jeff $300 and he's in Las Vegas and it's 11 o'clock at night. No problem. And at 2 a.m, it says, oh, you know what? Jeff pulled $300 a couple times here today. There's no more money left in his checking account. And they reconcile and go, whoops.
And actually, that's probably, if that were the case, I'm getting a new job. I'm doing that. There you go. I'm going to open up bank accounts and
right. That thought of our financial institutions do that reconciliation at shortly after midnight, off bank hours. That's a key example of that eventual consistency sync.
Yeah. And you can see that a lot too. You see it, like, for example, we travel a lot, or we used to until the COVID, and we'll travel again. But so here we are, we're booking a flight, we're in the Microsoft travel site, and you've probably seen this too, any travel site you use. You spend all this time, you find the right flight, you get the seats you want, the connecting flights, you're ready to go. At the very last minute, you say, here's your credit card, book the flight. And guess what happens? Sorry, but the flight's not available anymore. That's probably eventual consistency. The data you were seeing that you were booking for that flight is stale. Someone else has already bought that seat, right? And it just hadn't updated, and so
together with your wife, because somebody has 12C.
That's right. So you can sit in the back of the plane now by yourself. Here we go. I think what banks do sometimes, I think that whenever you do a withdrawal, that is pretty much consistent, but the deposits tend to be the things that don't always show up right away. Although they've gotten better. I remember a couple of years ago it used to be worse, but now it's gotten to the point, I think, where they're fairly consistent now.
They are getting better. So can I ask you a question here?
Sure.
Carol 82 has a question in chat. And they ask, if we implement CQRS, are all microservices then using a single read store?
No. Yeah. That's a really good question, by the way, too. This would be per microservice. So that's a beautiful question here, and I love that. So when we're looking at this particular, so we're flying at 10,000 feet and we see this, right? This would be maybe in our catalog or our ordering service. So within a microservice itself, we might implement this model. Now, if, for example, we wanted to have, if we had 2 or 3 microservices where this were applicable, each would have its own read store. The idea here is to keep the read store within the microservice, so everything's local. Because if we were to say, you know what, we got the service out here, this might be the inventory service, and it needs to get data from this read store, then we're back to the problem of making a cross-service or a synchronous call from one service to another. So what you would typically see here is if this write store, it could support a read store here, and it could also support a read store in this other microservice up here. So the eventual consistency would look more like this. We would update this particular write store. It would push that denormalized change to the read store in this service, and it might push also that denormalized change to a read store in another service. What's even more interesting about that is the actual read representation of the write data could be very different here than it is there. We may show certain fields here in a certain way in this particular service, but the same data could be expressed very differently in another service. So these read stores, they don't need to be the same. We're grabbing the core data, but in this process, we're going to transform that data to store it just how that particular service needs to see that data. And again, keep this in mind too, when we're doing CQRS, this would be maybe 1 or 2 tables. We may have within this service, within its data store, we could have, who knows, 10, 12, 15, 20 tables for that one service, more. Again, CQRS, we would only apply that to those particular data entities or tables that are really high volume. We're not going to do CQRS to everything, because again, that would be overkill. The CQRS can get complicated. So again, we want to really, I think, hold back and use that when we truly have high volume data entities where, again, our reads and writes are conflicting with each other on that. Or our reads are really slow, because the reason why we're storing this data, it is, one record is 8 or 9 joins. So every time we do a read against that, it's going to be slow, but if we can denormalize that and have a separate read store, we can make those reads really fast. So we can still have our denormalized representation, but we can keep our reads really, really quick on that, if that makes sense. I'll point out something really quickly here, and I'll close on this as well too, because it is getting kind of late for everybody. In the application, we just started putting CQRS in the ordering service. You'll see it is if you actually go into the app, let me kind of zoom in here. This is the ordering service. You'll notice that there are actually 2 repositories. There is a NoSQL repository and a relational database, a relational repository in the ordering service. What we do here is you write all the data goes to the relational database. We've got a nice, if you look at our representation in here, we have I could go into SQL Server and show you, but just kind of give you a little preview. We have a here we go. We have an order table, an order detail table, an order status table, a payment method table, a buyer. These are all joined together, if you will, or these are all individually represented, in our relational database. In our NoSQL database, we have a let me show you that real fast. We basically crunch that data, or crush it into a single representation. Let me show you real fast. This is what it looks like if I go into conf. We put it in Cosmos DB. Let me go to Cosmos DB, which is going to be right over, where is it? Cosmos DB right here. Cosmos DB, if you don't know, this is a NoSQL data store that's available in Azure as a managed service, very robust. It can do MongoDB workloads, Gremlin workloads, Cassandra workloads. It's very, very robust. It is a talk in and of itself. But again, this is what the actual data looks like. So here's our order collection. This is a song here. Let's look at one here. This is a song that is. This is how we basically store the data in our read model. It's all a single document. So this is one order right here. So the order is from Prince Fossey, that's his name, in Ohio. He bought Carry On by Chris Cornell. Here's the order date. Here's the total. So you can see when I'm querying an order, I'm not joining together 5 tables. I'm going against this nice normalized representation of data. Here's one, for example. Here's one where we have one song. I think if you buy them all, here's an order where we have 3 songs. So again, this is from Britt Kilbride in Ohio. Bought 3 songs. You can see again. But the idea here is if we could look in the relational database, everything, we have separate tables for all this. In the NoSQL, everything is denormalized into a single document. So when we're reading data out of this Cosmos, it's super quick. We're not having to join tables together and then and bring it back. Everything's already denormalized for us. So on that happy note, I hope this helped. We talked about a lot of stuff today, Jeff. We talked about We talked about microservices in general. We talked about benefits. We talked about some of the challenges. We touched upon some of the modeling concerns when we're doing greenfield and brownfield. We talked about architecture. We talked about service design. We talked about backing services and what they are and how they work. We talked a little bit about logging and how important that is and how we need to correlate the logging across all these services. We got into communication. We talked about front-end client communication. We talked about service-to-service communication. Manu took us to a great set of information in terms of, what are containers, what is Kubernetes, what does it look like, what are service messages. And then we ended up talking about data and how we deal with data. When we have separate data in each service, how we do transactions, how we do querying, and how we deal with high volume. I hope this helped. Thanks for staying with us. Closing thoughts. You go. I think that says it all right there.
Yeah. Gosh.
Thank you, guys.
Yeah.
Thanks, everybody. Manu, Jeff, thanks, everybody.
Thank you so much. Can you guys hear me?
Yes, we can.
Yes.
Oh, okay. My machine is muted. But yeah, thank you, Rob, for great work, and thank you, Jeff. This was fantastic.
Yeah, and
we're going to make these. Go right ahead, Jeff.
I was going to say, right, we're going to make the slides. We're going to make the code available along with the recording sometime next week. Keep an eye on the .NET channel on YouTube. Go and subscribe out there. We'll publish all the material out there for the recording, and watch the .NET Conf website. We'll update it with information as well.
Right, and what we'll do too is we'll go through. I think there's been a lot of questions that we haven't been able to answer. We'll start looking at them and trying to get back to you with answers on that stuff as well too. Thanks for your time. Appreciate it. I hope this helped.
All right, everybody.
Jeff. Thank you for all your time. Manu, Beth Mazzy helped a lot. A lot of people, Nishanil, Scott Hunter, everybody for making this happen. It was great. Thank you so much.
All righty. Well, take care, friends. You have a good weekend, and we'll see you for our next .NET Conf event coming up in November. We've got the full .NET Conf event, and we're going to announce the RTM of .NET 5 at it. All right. We will see you in November. Take care.
Be safe, everybody.